Welcome again. Today I will solve the questions of ordinary differential equations using the Laplace transformation. We know that the Laplace of f dash t is equal to s into Laplace of ft minus f0. We have proved this formula in our earlier lecture, and this was your s square Laplace of ft minus s f0 minus f dash 0. So let us replace our ft by yt. So the Laplace of y dash t will be equal to s Laplace of yt minus y0. Then we will have Laplace of y double dash t as s square Laplace of yt minus s y0 minus y dash 0. Again, we have the formula of Laplace tft, which was your minus d by ds of Laplace ft. So using this formula, we have the Laplace of t into yt is equal to minus d by ds of Laplace yt. So now we will use this formula to find out the Laplace to evaluate the differential equation. So in place of yt we can have some function of, we can have x of t or some other function. So let us start with question number 1. Solve. We have the question y double dash minus 4y dash plus 3y equal to e to the power minus t, where our y0 is 1 and y dash is 0. Okay. Now we have to solve this question using the Laplace transformation. Solution. Let us take Laplace transform. Then this will be your Laplace y double dash minus 4 times Laplace y dash plus 3 Laplace y is equal to e to the power minus t. Please remember that our y dash is dy upon dt. We can also have x in place of y. That means x dash in place of y dash. So the Laplace of y double dash will be s square y bar minus s y0 minus y dash 0. Then we will have 4 s y bar minus y0. Then 3 y bar, and the Laplace of e to the power minus t is equal to 1 upon s plus 1. Here we have taken y bar in place of Laplace y. We have denoted Laplace of y as y bar. So as y0 is 1, so this will be equal to s square y bar. y0 is 1, so this will be your minus s, y dash is 0, and here we will have minus 4s y bar plus 3y bar, and y0 is 1, so this will be your plus 4 is equal to 1 upon s plus 1. Now we can take y bar common, so we will have s square minus 4s plus 3 y bar. Now you can take this term in the right hand side. So in the right hand side we will have minus 4 plus s and then 1 upon s plus 1. So let us simplify right hand side. In the left hand side, this is your s minus 1 into s minus 3 into y bar. So this is your s minus 1, s minus 3. Now in the right hand side, let us take the LCM. So we will have minus 4 s minus 4 plus s square plus s plus 1 divided by s plus 1. So our y bar will be equal to s square. This will be minus 3s minus 4 plus 1 will be minus 3 divided by s plus 1, s minus 1, s minus 3. Okay, now let us compute the inverse Laplace transformation. As our y bar was Laplace of yt, so we will need the inverse Laplace transformation of the right hand side. Now to evaluate its inverse Laplace transformation, let us have its partial fraction. Now the partial fraction of this term will be equal to, say, a upon some s minus 1 plus b upon s plus 1 and then c upon s minus 3. So let us take LCM. So in the left hand side we will have s square minus 3s minus 3, then a into s plus 1 s minus 3, b into s minus 1 s minus 3 plus c into s minus 1 s plus 1. Now one by one we will put s equal to 1. So if s equal to 1, then this term will be 0. Again it is 0. So if s equal to 1, then this will be your 2, and here we will have 1 minus 2. So this is your 2 into 1 minus 2, that means minus 4a equal to, now if s is 1, then this will be your minus 3 plus 1, that means minus 6 plus 1 means minus 5. So your a is 5.4. If s equal to minus 1, now if s is minus 1, then this term will be 0. Again it is 0. So here we will have minus 1, that means minus 2. And then here we will have minus 1, minus 3, that means minus 4. So 4 to the 8, v equal to, now as s is minus 1, so this will be a 3 plus 3, 3 minus 3, that is 0. So we will have 1. So v is 1 by 8. Now if s is equal to 3, now if s equal to 3, then this term is 0, again it is 0, so this will be 4 to the 8, 8 into c equal to, this will be your 9. Now s is 3, so this is 9 minus 3. So 9 minus 9 is 0, so in the right hand side we will have minus 3, so c is your minus 3.8. Hence our partial fraction will be, thus we can say that the Laplace yt is equal to the Laplace inverse of this bracket, and it is equal to a was your 5 by 4, so the 5 by 4 into Laplace inverse of 1 upon s minus 1. Then we have b, and b was 1 by 8, the Laplace inverse of s plus 1. Then c is minus 3 by 8, then the Laplace inverse of 1 upon s minus 3. So our answer is 5 upon 4. The Laplace inverse of 1 upon s minus 1 is e to power t. The Laplace inverse of 1 upon s plus 1 is e to power minus t. And the Laplace inverse of 1 upon s minus 3 is e to power 3t. So this is your answer. Let me verify it. So we have 5 by 4 e to power t, 1 by 8 e to power minus t, and minus 3 by 8 e to power 30t. So this is your final answer. Let us solve another question. So solve ty double dash plus 2y dash, then ty equal to cos t, where my y dash 0 is 1. So where my y0 is 1. Let us solve this question. Ty equal to cos t. So let us solve this question. Solution. Taking the Laplace transformation, we will get Laplace dy double dash t plus Laplace y dash plus Laplace dy is equal to Laplace cos t. Now use the formula. The Laplace of ty double dash was s square into Laplace of yt, which is your y bar minus s y0. Okay. Before using the Laplace of y double dash t, we have the formula of Laplace t ft. The Laplace of t ft was minus d by ds of ft, means the Laplace of y double dash. Now we will have to remove this t. To remove this t, we will use this formula. That means the Laplace of t into ft equal to minus d by ds of Laplace ft. Now ft means the Laplace of y double dash plus 2 Laplace y dash. Again here we will use the Laplace of ty, that means minus d by ds of Laplace of y. And the Laplace of cos t is s upon s square plus 1. So this is your s square y bar minus s y0, y0 is 1, minus y dash 0. Now y dash 0 will be constant, so its derivative will be 0. So this term will not create any problem because its derivative will be 0. 2 Laplace of y dash will be s y bar minus y0, which is your 1. Say Laplace of y as y bar, then this will be your dy bar upon ds equal to s upon s square plus 1, where y bar is the Laplace of yt. Now let us differentiate this equation. The differentiation of s square will be minus s square will be 2s, then we have the minus sign into y bar minus s square dy bar upon ds. We have used the product rule. Differentiation of s square will be 2s, then we have y bar, now plus s square into dy bar upon ds. As we have minus sign outside, so we will have terms with negative sign. Then the derivative of s will be 1, so minus minus plus, this will be 1, and the derivative of y dash 0 will be constant because y dash 0 will have some constant value. Now here this will be a 2 sy bar minus 2 minus dy bar upon ds equal to s upon s square plus 1. So this is equal to, now this term will be cancelled with this one, so minus 1 plus s square dy bar upon ds. Now this is your minus 1, so this on the right hand side it will give 1, so 1 upon s square plus 1. So minus dy bar upon ds will be equal to 1 upon s square plus 1 plus s upon s square plus 1 whole square. Please note that we have a formula of Laplace inverse minus d by ds fs as t into Laplace of ft. Now here we will use this particular formula. So this was t into ft. Here we will use the formula that Laplace inverse of minus d by ds of fs is equal to t into ft. So taking the inverse Laplace on whole side, both sides, taking inverse Laplace transform. So on taking the inverse Laplace transformation, we will get Laplace inverse minus dy bar upon ds is equal to Laplace inverse of 1 upon s square plus 1, then the Laplace inverse of s upon s square plus 1 whole square. Now if you do not want to take this, if you do not want to use this formula, then we will have to integrate this equation first with respect to s, then later on we will find its inverse Laplace transform, but that will be tedious. So I am using this particular formula. Now this Laplace inverse of minus dy upon ds will be t into yt. So this will be your t into yt because the Laplace inverse of y bar is your yt, and the Laplace inverse of 1 upon s square plus 1 is sin t, and again you know that the Laplace inverse of s upon s square plus 1 whole square is t upon 2a. We have already proved this result. that the Laplace inverse of s upon s square plus a square whole square is equal to t upon 2a sin a t. We have already done it. So our answer is yt is equal to sin t, and then in the bracket we will have 1 by t plus t by 2. So this is your answer. Now let us start with another question. Solve y double dash plus 2y dash plus minus 4y is equal to 1, where our y0 and y dash 0 is 0. So let us solve this question. Again, take the Laplace transformation. So on taking the Laplace transformation, we will get Laplace y double dash plus 2 Laplace dy dash minus 4 Laplace of y is equal to Laplace of 1. Now we have the formula of Laplace y double dash, which was your s square y bar minus sy0 minus y dash 0. Now both y0 and y dash 0 are 0, so they will not create any problem. Plus, now here we will use the Laplace of tft. The Laplace of tft is minus d by ds of Laplace of y dash. Then we will have 4y bar, and the Laplace of 1 is 1 by s. So this is your 0, that is 0. So this will be your s square y bar minus 2 times. Here Laplace of y dash is sy bar minus y0, which is your 0. So we will have this term. So from here we will get s square y bar minus 2. Now here the differentiation will be 1. Then we will differentiate this one. So this will be your dy bar upon ds minus 4y bar equal to 1 by s. So let us take this y dv. Let us take this y bar as common. So in the bracket we will have s square minus 6. This is your minus 2, that is your minus 4 y bar equal to 1 by s. Then now you can see that it is a linear differential equation of first order. So this can be written as dy bar upon ds. Then here we can write it as 6 minus s square divided by 2s into y bar equal to minus 1 upon 2s square. So clearly you can see that this is of the type dy by dx plus p some function of x into y equal to some function of x. So the solution of this particular differential equation will be, solution is y bar into integrating factor equal to, in the right hand side, minus 1 upon 2s square into integrating factor into ds plus some constant of integration. So this is the solution. Now let us compute the integrating factor, where integrating factor means e to power integration of 6 minus s square divided by 2s ds. Now you can see that this will be your e to power integration of 3 upon s minus integration of s upon 2. So the integration of 3 upon s will be 3 log s, and the integration of s upon 2, integration of s will be s square by 2, so this will be your s square by 4. Here we have separated these terms because we know that this can be written as s cube log s cube into e to power minus s square upon 4. As we know that e to power log x is same as x, so this will be your s cube into e to power minus s square by 4. Thus our solution is, so this is equal to y bar into s cube e to power minus s square upon 4 equal to minus 1 upon 2 s square s cube e to power minus s square upon 4 plus some constant of integration, and this is equal to minus s upon 2 e to power minus s square upon 4 ds plus c. You can see that if s square minus s square upon 4 equal to t, then this will be your minus s upon 2 ds will be dt. So you can see that this is your e to the power t, and minus s upon 2 ds is dt. So this is basically e to the power t into dt, and the integration of e to the power t is e to the power t. So our answer will be y bar s cube e to the power minus s square upon 4 equal to, this was your just e to the power t, and the integration of e to the power t is e to the power t plus some constant of integration. Now let us divide this whole equation by this term. So our y bar will be 1 upon s cube plus c on s cube e to the power s square by 4. Please note that as Laplace of yt tends to 0, as s tends to infinity, hence this c must be 0. Why? We know that Laplace of yt equal to integral 0 to infinity e to the power minus st ft dt. Now as s tends to 0, the Laplace of yt has to be 0. Now Laplace of yt means y bar. So as s tends to infinity, this has to be 0. Now for the first one there is no problem. As s tends to infinity, this will be a 1 upon infinity, that is 0. But here we will have a problem. Now as s tends to infinity, this will be your infinity. Again here we will have e to the power infinity, which is your infinity. Now this is of the type infinity upon infinity. Now to tackle with this term, this c must be vanish. If this c is not 0, then our solution will not converge. So this c has to be 0. Therefore our y bar equal to 1 upon s cube. So we can say that our yt is Laplace inverse of 1 upon s cube, which is your t square upon 2, and obviously your t has to be greater than or equal to 0. Now we can solve simultaneous differential equation using the Laplace transformation. I am not solving this question. I will give you this question for your reference. Let us solve dx upon dt plus y equal to sin t, and dy upon dt plus x equal to cos t, where x equal to 2, y equal to 0, and t equal to 0. You can easily solve this question just taking the Laplace transformation of these two equations. So I am not solving this question. Now let us solve integral equation using the Laplace transformation equation. Let us solve this equation. Say yt equal to 1, or you can take any other variable, say t, integral 0 to t y of u cos or maybe sin t minus u du. So this is a special type of integral equation. We can solve such type of integral equations using the Laplace transformation. So Laplace transformation has this type of application. So taking Laplace transformation, the Laplace of yt will be the Laplace of t. The Laplace of t is 1 by s square, and here we will have the Laplace of integral 0 to t yu sin t minus u du. And we know that the Laplace of, using the convolution theorem, the Laplace of integral 0 to t fu gt minus u is equal to fs. Fs means the Laplace of y. The Laplace of y is y bar into the Laplace of sin t, and the Laplace of sin t is 1 upon s square plus 1. So in the left hand side we will have y bar, in the right hand side we will have 1 upon s square minus y bar upon s square plus 1. So we will have y bar 1 minus 1 upon s square plus 1 equal to 1 upon s square. So this is your s square plus 1 minus 1. That means in the numerator we will have s square upon s square plus 1 equal to 1 upon s square. So our yt is equal to, our y bar equal to s square plus 1 upon s4. So this is equal to 1 upon s square plus 1 upon s power 4. Now just take the inverse Laplace transformation. So the inverse Laplace transformation of this y bar will be Laplace inverse of 1 upon s square plus Laplace inverse of 1 upon s4. Now we have the formula for the Laplace inverse of 1 by s square. The Laplace inverse of 1 upon s square is t, and the Laplace inverse of 1 upon s4 is t cube upon factorial 3, that is your 1 by 6. So this is your answer. Now thank you guys for being with me for the last 1 week. Now in the next week I will solve some questions related to the Fourier series, and in the meanwhile if you have any problem then you can ask me through the comment box. Thank you.